Hello everyone, and welcome to a video tutorial over the free response that we were going over today. So I could sense your confusion because of all of the variables, so I'm here to let you actually see what's happening. So here we've got our projectile launcher, projectile. This is in place of our block that was having the wood or the bullet penetrate. And here with this trial I've got it locked in place by these two weights behind it. So we fire, and we can see that the bullet penetrates at a certain distance. Now, if I repeat the experiment, but I allow the apparatus to slide back, we should notice a difference in the depth of penetration by the projectile. So if I set this up and fire again, it doesn't even go in far enough to stick into the apparatus. So that tells me that when this is free to move, the penetration distance is lower. Now, why is that? Come over here, step into my studio, and we can see why that happens. So here's a basic setup of our first trial. So we had a projectile of mass M and a kind of a base with a mass capital M. It penetrated a certain distance, and I'll call that distance D. Okay. The projectile had an initial energy, and the block did a certain amount of work to stop it. So if we figure the conservation of energy, K1 plus U1 plus the work done equals K2 plus U2. Well, there was no change in height, so therefore there is no change in potential energy. So go ahead and cross those off. And my final kinetic energy would be 0 because this was fixed in place, so there was nowhere for the bullet or the block to go once it stopped. So I have no final kinetic. So in other words, 1/2 little m v squared, I'll call that v initial, we'll say it leaves the projectile with some initial velocity, plus the work done equals 0. Now that work is going to be the work done by the block. Now, the block is going to exert a force on the bullet, and work is F delta R cosine theta. Now, KE is always positive. So in order for this to be 0, this work has to be negative. Why that works out is you think cosine theta. That theta is the angle between the force and how the bullet moved. So the bullet moved this way into the block. Friction had to be in the opposite direction. So I have 1/2 m v naught squared minus the force, which was just whatever force was from the block, times d equals 0. Okay, that's our setup for the first situation. Now, in the second trial that we did, our block bullet system was not fixed in place. So we still had the same two blocks and the same initial velocity. But after the two collided, the bullet embedded a certain distance, which I think in the free response it called dn, but the block slid a distance d from its original position. How does that happen? Well, if you figure conservation of energy again, well, now there is more than one thing doing work. So there's still no change in potential, and there's still no final kinetic. And I have the same amount of initial kinetic energy. But I now have a new distance, dn, which we could measure, and it would be lower than our previous distance, d. Now, the only way that could happen is if you figure, okay, well, we subtracted the force of the block times this new distance dn. But dn is smaller than d, which means this isn't going to get me to 0. Which means there is another work done, and that is the work done by, in our case, the ramp or the table or whatever, the frictional force here, Fk, on the housing block. So minus Fk, capital D. That is going to get me to 0. So here you have mass, velocity, the force of the block, this new penetration distance, friction, and then the distance that the block slid. Those are your variables and those are your unknowns, and this is from a conservation of energy standpoint. You could also look at it from a conservation of momentum standpoint. So the two objects start separate and then end together. M1 plus M2 times V. This is little m, big M, so on and so forth, no initial velocity. So from here, you could think, okay, velocity, well, I know that that is related to kinetic energy. Solve for V with kinetic energy in the previous example, and you'll be able to solve for this using the masses.